Ever wonder how a simple magnifying glass actually works? Or how a giant telescope lets us peek at galaxies billions of light years away? Well, it all boils down to just a few really elegant rules that tell light where to go. So today, we're going to decode those rules and see how we've learned to master them. But before we get into all that, let's start with something, well, something you're probably using right now. How in the world can a single, thin strand of glass carry pretty much the entire internet? It sounds impossible, doesn't it? Stick with me, because the answer lies in understanding light's incredible journey, and by the end of this, you'll know exactly how it's done. All right, to understand all the cool tricks light can do, we have to start with the most basic rule of all, the absolute foundation for everything else we're going to talk about, light's simple straight path. There's a whole field of study for this called ray optics, and the core idea, it couldn't be simpler. We just pretend that light is made up of a bunch of perfectly straight lines, or rays. Now, yeah, technically light is a wave, but for most of the things we see and interact with, its wavelength is so tiny that just thinking of it as a straight ray works perfectly. So this is the big takeaway. Unless something gets in its way, light just travels in a dead straight line. And it does this at a speed that's, well, it's hard to even wrap your head around. Almost 300 million meters every single second in a vacuum. It's the universe's ultimate speed limit, and it's our starting point for understanding everything we see. Okay, so we've established that light travels in straight lines. The next logical question is, what happens when one of those lines hits something it can't go through? Like a mirror. Well, that brings us to our next big idea, the law of reflection. It reflects, it bounces off, and it follows this one beautifully simple law. The angle the light comes in at, we call that the angle of incidence, is exactly the same as the angle it bounces off at. Honestly, you can just think of it like a perfect bank shot in a game of pool. Simple as that. Now, here's where we start to play with that rule. By curving the mirror, we can actually control where the light goes. A concave mirror, the kind that's curved inward like a cave, makes all the parallel rays bounce and meet up at a single focus point. But a convex mirror, one that bulges outward, does the exact opposite. It makes all the rays spread out. This simple trick is behind everything from the magnifying mirror in your bathroom to the side view mirror on your car. But light doesn't always bounce off, right? I mean, it goes through windows. So what happens when it travels from one clear material, like the air, into another one, like water? This leads us straight to the law of refraction. It refracts, which is really just a fancy way of saying it bends. See, light actually changes speed when it moves into a different substance, and that change in speed makes it change direction. You've totally seen this before. You put a straw in a glass of water, and it looks like it's broken right at the surface. That's not a magic trick. That's refraction. Now, this bending isn't just random chaos. Nope, it follows a super precise rule that was figured out centuries ago, and it's called Snell's law. Now, don't worry about the math here. The important thing is that this law gives us a predictable way to know exactly how much the light is going to bend when it goes between any two materials. And this is where refraction becomes a superpower. Because if you can control how much light bends, you can carefully shape a piece of glass into a lens and use it to focus light. Every single lens, the one in your glasses, the one in a camera, even the tiny ones in your own eyes, they all work because of this one fundamental principle. So, light can bounce off things, or it can bend through them, but what if you could kind of combine these ideas? Well, that leads to a really strange and incredibly powerful phenomenon. It's almost like a magic trick. You can literally trap light. So just imagine a ray of light trying to travel from water back out into the air. We know it's going to bend. But what happens if you keep increasing the angle it hits that surface at? What happens when it bends more and more and more? Let's walk through it. At a shallow angle, the ray bends a little and escapes into the air. No problem. As we increase that angle, it bends more until, bam, it hits what we call the critical angle. Right there, it bends so much it just skims perfectly along the surface. So what happens if we go just one tiny degree past that? The light can't escape at all. It gets perfectly reflected right back into the water. We call that total internal reflection. So that critical angle, that's the whole key. It's the tipping point, the angle of no return. Go past that angle, and suddenly, the boundary between the water and the air stops being a window and starts acting like a perfect mirror. And get this, every material has its own unique critical angle. Just look at diamond. Its critical angle is incredibly small, only about 24 degrees. This means that almost any light that goes into a diamond gets trapped inside, bouncing around like a pinball over and over again before it can finally find an exit. That is what gives a diamond its famous sparkle. And total internal reflection isn't just pretty, it's unbelievably efficient. I mean, look at this. A specially made silica glass fiber can transmit over 95% of a light signal down a full kilometer. That's a shockingly tiny amount of signal loss. It's practically perfect reflection. And that brings us right back to our original question. The internet is carried by little pulses of light shooting down fiber optic cables. Every single pulse hits the inside wall of that glass fiber at an angle greater than the critical angle, causing it to reflect perfectly, again and again and again, for thousands of miles. We have literally trapped light to build our digital world. Okay, so we've seen how light reflects and how it can be trapped, but what happens when we really focus on the bending part? In our final section, let's look at how harnessing light with lenses has given us some of our most important tools. And just like with mirrors, we basically have two main types of lenses. You've got convex lenses, the ones that are thicker in the middle, and they bring light together or converge it to a single focal point. These are your magnifying glasses. Then you have concave lenses, which are thinner in the middle, and they do the opposite. They spread light out or diverge it. And the applications? Oh man, they are everywhere. We use lenses and microscopes to see whole worlds that are invisibly small. We use them in telescopes to explore the cosmos, in cameras to freeze a moment in time. And for millions of us, we put them in glasses and contacts, just so we can see the world clearly every single day. And by combining lenses, we can get some really incredible results. A simple magnifying glass, it might make something look about 9 times bigger. But a compound microscope, which uses one lens to create an image and then a second lens to magnify that image, you can get magnifications of 250 times or even more. But it's kind of funny. For looking at the stars, the biggest, most powerful telescopes today have actually gone back to using mirrors instead of lenses. Why? Because a giant, curved mirror can gather way more light than a lens of the same size, and that lets astronomers see these incredibly faint and distant objects at the very edge of the known universe. So think about it. Starting from that one simple rule, that light travels in a straight line, we figured out how to bend it to help us see, how to reflect it with mirrors, and even how to trap it to send information all around the globe. It really makes you wonder, with these incredible principles in our hands, what on earth are we going to see next?